how much should we distance ourselves from asking for ideas from professors or industry professionals and the like?
You can definitely ask for ideas.
Oh, we can, okay.
Yeah.
If your school doesn't have facilities for what you're trying to do, would you approach commercial facilities nearby the same way?
For sure.
Just like, hey, we're doing this thing, it'd be super cool if we could use your vibration cable.
Yes, this is the exact same strategy of going and asking for money from external people, or the same strategy as asking for facility access from facilities within the university. That same strategy applies going externally. Whether it's other companies, whether it's that might have facilities themselves, whether it is test facility places, things like that. Especially being able to throw that student flag and, hey, we're learning, we're trying to do this sort of thing, especially for companies. They want you to learn this sort of stuff because that's what makes you valuable later, which then they get excited about for being able to hire you later. So.
Thanks.
Okay. Otherwise, other than resources and equipment and things like that, the other key thing is advisors. Even Astranis or any of the other companies that I've worked at where we have people with a huge amount of experience, we still go and spend a lot of time finding advisors and getting people to help us out with things that we aren't aware of. Even if very experienced people at companies are doing that, then you guys absolutely should be doing that. Yes.
I think that you said that studying or whatever is building these things isn't like an exam. You can go ask for help, and you should. Absolutely.
Yeah. Both for this project and also when you go and do internships and jobs, there's a very big difference between classes where you're not supposed to leave with your partner. And yes, ask for help for this and in general with like jobs and internships and all the things. Yes.
So there's like no limit to how much help we can receive?
No.
Oh, okay.
Get everything you can get.
Yeah. So for advisors, would they have to be faculty members of our university, or could they be like any sort of figure?
Anybody. Faculty members are good. I mean, the best type of advisor you're looking for are people that have built something that is similar or harder even, or whatever, similar to what you're building now. So whether that means people that have built spacecraft before, or people that have built power systems before, or people that have built, I don't know if you're doing some sort of imaging thing, people that have built imaging systems before. It doesn't have to be space related at all, but some combination of people that have built various space things, various satellites, or various things that are similar in design to what you've built. Yeah.
So this is an Astranis back competition. Would it be stepping on your toes to get money from other commercial companies to sponsor this, or?
Not at all.
Okay.
No. I think you guys should feel very empowered to go find money from wherever you can. Go find advisors from wherever you can. All these sort of resources. Yeah.
If multiple universities or multiple census chapters wanted to do like a unified proposal as like single CubeSat 2 universities, would that be accepted as well?
I personally would be supportive of that, but
I couldn't hear it. Sorry.
If multiple schools wanted to come together to submit a single proposal,
I think that's absolutely awesome. Yeah.
All right, so now you know roughly what you want to build, you know roughly, or maybe you have some idea of what sort of resources you have available. So next step is, you don't want to, it's really, sometimes it's very scary to figure out how are you going to get from blank slate to getting to, hey, what is our design roughly going to look like? And the way that I found this to be most useful is to just start as simple as possible. So now you have a payload, you know presumably some idea of how much mass it's going to have, how much power it's going to have, what sort of space it's going to require, things like that. So once you go from that, you can use some very basic kind of calculations and things like that to figure out, okay, what do I need? So you can go from, okay, I need this much power, I need to be operating it at this much time. You can then back out, okay, I'm going to need this much solar area, I'm going to need this much batteries, I'm going to need kind of these other systems that support it in various different ways. If you guys aren't aware, a book that I would highly, highly recommend is SMAD, Spacecraft Mission Analysis and Design. It's a book that has, it's a little bit hedged towards the traditional aerospace way of doing things, but at the same time, the fundamental equations and calculations for all this sort of stuff is the same for any spacecraft. And so if you aren't aware of that, or you haven't seen this sort of material from classes or anything like that, definitely grab that book, and that'll walk you through a lot of these basic sizing, initial description of how you design and how you make components for a lot of these different subsystems and the spacecraft as a whole. So running through, some of this is just basic hand calculations, some of it is starting to put together your budgets and things like that, and starting to just flow together, okay, getting a feel really quickly of what does my spacecraft need in order to work, in order to do what I said I wanted to do. Okay, I'm not sure what I meant by the next bullet, so I'll skip that one. Roll up budgets. So the next one is, as I was saying before, as you're starting to do all this sizing, the next thing is to just understand what your budgets are, what you're gonna have. Now budget, there's lots of types of budgets. Obviously, when you hear the word budget, first thing you think of is money. So that's obviously important. You know how much money you're gonna be able to get. You know that that's sort of a constraint that you have. But there's so many other types of budgets. Your time, schedule is a budget, like I talked about before. Then you have all of your technical budgets, your mass budget, your volume budget, your power budget, link budget, and various others, thermal. So what you should be doing at this point, once you have a basic idea of what you're looking at, you should really just have lists of all of these budgets that are summing up per subsystem, and considering how much you also know, how much you trust these different numbers. Because, for example, if you make rough estimates of something, then you're probably going to be estimating low. So it would be good to take that into account, your sort of current best estimate versus like a margin number, and then you don't necessarily have to design things to your margin number, but you should be aware of what your uncertainty bounds look like. And so I just started putting together a list of that and started rolling things up. Next up, so now you know roughly what you're building, you know maybe an idea of what things you're going to be buying, what things you're going to be building. So now I'm going to talk a little bit more about the building side of things. So when you're building things, kind of the key things is to start early and iterate often. One of the things that is really, really frustrating, we see people doing, is that you can go years or decades of what I call PowerPoint engineering, going and essentially purely by analysis, purely by hand calcs, purely by doing stuff in CAD, purely by making pretty pictures, go through and design and make things that exist only in electronic format. And what you really need to be doing if you want to be finding out A, if things are going to be working, and B, just getting you toward detailed design, is just build something. Maybe you don't know all the details. Maybe the first thing isn't fully worked out. You haven't done enough analysis. You don't know exactly how it's going to work. Well, the way you're going to figure out how it's going to work is because you build the thing and then you test it. So build early, iterate often for these things that you're building yourselves. And then as you're building the spacecraft together, and that's the same thing. Even if maybe, let's say you are buying a few components, buying a battery, buying a power system, until now these things have long leads. So if you're buying a power system, that lead time, you might, after you place the order, we're not talking about going to McMaster, we're not talking about going to the local brick and mortar store or whatever. This thing could take 4 months for you to get it. And so that's a problem. So how do you get around that? You should be building surrogates. You should be building something that you can use to test in the meantime, to do your integrated system testing. So let's say you've built some rough prototype of your payload, but you're going to be buying a power system. So you can simulate that power system until you get it using power supplies. Just buy some lithium-ion batteries off the shelf and use that as a, off Amazon or something even, and you can hook those together as long as you have the correct protection circuitry. Batteries, be very careful about batteries. As long as you know what you're doing, and as long as it says correct protection circuitry in it, build simulators and build surrogates for these systems, and that can be done very inexpensively, and you can put together something without a huge amount of effort to simulate that while you're waiting for these long lead time components to come in. And the next thing is, as you're doing this prototyping, as you're deciding how much hardware you want to be building and how much hardware you want to be buying, make sure you consider that you're going to need flight hardware and you're going to need non-flight hardware. Again, on this whole testing thing, if you want to believe that you're going to be able to, if you believe that your flight vehicle is going to work, the best way for you to gain confidence that it's going to work is that you have a non-flight set of hardware and you feed it really, really dirty things to it. You want to take it to what you expect it to do, and then you want to go beyond that. If you think that your temperature environment is going to be minus 40 C to 50 C, you should hit that thing with like minus 60 to 70 C or something like that. If you think that that this thing is going to see voltages, I mean, if you think this thing is going to see currents that max out at half an amp, you should like run an amp through it. Obviously, kind of very case-by-case basis on how much, what sort of fractions or margins you can, and factors you can put on top of this. But in general, or maybe a better example, if you think that you need to be running this thing for an hour a day, you should be running day-in-the-life simulations where the thing's going for 3 hours a day and see what happens. And watch it pull your battery down, and watch your battery go into under-voltage protection, and then get charged back up and make sure that it does all these things. You don't want to do this on your flight hardware because tripping your battery into under voltage will significantly degrade your capacity. But you should learn what the systems can do. And the reason I bring that up in particular is that getting a second copy of the hardware you're building isn't necessarily that expensive. But when you're procuring hardware, make sure you take that into account in your budgeting, and your decision about whether you can afford to procure this hardware should really be buying 2 copies. And the second reason for that is when things go wrong on orbit, because they will, you need something that you can debug on the ground and play with, and then gain an understanding of, this is what's happening, because I can actually poke a multimeter at this thing that's on the ground, but I can't poke a multimeter at the thing on orbit. Yeah.
Kind of speaking to the buy 2 copies, should we actually be buying 3 if we want to do, like, beat one up, have one actually fly, and then have one for debugging, or do you think that it's kind of enough to beat it up and still rely on it? What do you recommend?
If you can afford it, that's awesome. But I think it's reasonably excessive. The main thing for when you want to get 3 is if you have a large team and you just want to not be blocked by having hardware available, that's when you would start to have more than 2 available. I would say that having 2 is the bare minimum to sort of be critical, and especially on strapped student budgets, I think you're probably going to probably not have more than 2. For certain things that you're buying, it'll be probably relatively easy, but if you are buying subsystems, I think it'll probably be hard unless you're in a very good fiscal situation. Otherwise, test. Like I said, test. A little bit here on some subsystems. Just wanted to list out things, make sure you guys are aware of this. Going through things like SMAD will be super valuable for you being able to see what subsystems you need, how they link together, what sort of calculations you need to size them to determine what capacity and requirements you have. Payload, what's your satellite going to do? Obviously the most custom thing on your vehicle. Power, what sort of solar arrays do you need? What sort of batteries do you need? What sort of power distribution system do you need? This is something relatively common, of something you can buy off the shelf. Definitely would consider that. Also something that you can build. Guidance, navigation, and control. So what this looks like is how are you going to determine where you're pointing, what your attitude is, and then how are you going to control that? So determination are things like your sun sensors, maybe even star trackers, magnetometers, things like that. How you're going to control that, generally torque coils and radiator wheels. All things that you can buy. I would definitely not recommend building all of these things. That would be a lot of work. So it might be, you can either buy units that are kind of fully integrated and does a lot of this for you, or you can do piecemeal. You build some of it, you buy some of it. Avionics, flight computer, plus all of the support circuitry. You can buy a flight computer, you can build a flight computer, either reasonably options. If you're buying one, you'll probably need some breakout capability to make it so that this off-the-shelf flight computer is able to interface with all of your custom system. Mechanical, you can buy structures, especially for a 1U CubeSat. It's very easy to go off and buy a structure. That structure may or may not work for you. If it doesn't work for you, and you listen mechanically inclined people, then it's a relatively straightforward thing to build yourself. Thermal, probably not going to be too huge of a deal. Fortunately, in low Earth orbit, you have a good view factor of the Earth, which gives you some infrared radiation, which keeps you reasonably warm. As long as your payload is not running at a huge duty cycle, you shouldn't be getting too hot. That said, a little bit of some basic hand calculations on making sure that you're not going to freeze or burn up is critical to think about. And again, SMAD can help you out with some of that. Finally, software. All the hardware does nothing, so you don't have software that's telling you what to do. You can get some help from some of the software if you're buying a flight computer, buying avionics from somebody else. If not, then obviously something that you'll need to make sure that you're thinking about. It tends to be one of the things that's not thought about until later, and tends to, in a lot of cases, actually drive your hardware availability, is having software that can work. So something to make sure you're not forgetting about. Okay, so now that I've gone through all of that and we've spent quite a bit of time on all that, I'll run really quickly, show some pictures and any particular lessons learned that I think about. So just a couple of example programs. Planet, for anybody who's not familiar with, who's familiar with Planet? Okay. Who's familiar with Astranis? Okay, so Planet, Doug's doing 3 CubeSats for remote sensing. And so the idea is that essentially the front 2/3 of the spacecraft are essentially a telescope used for imaging the Earth. So we're building these. One key thing that I wanted to show here was just the sort of iteration between this and this. And just to go and sort of support some of the statements I was saying before of build something early and iterate. Planet very much did the sort of thing where it was build something as simple as you possibly can and then kind of go from there. And really just getting a basic product together that has all of the required features, even if it's kind of crappy, it gives you a lot of value, and then being able to have an integrated system and then be able to improve all different things is much more tractable than trying to go and say, oh, we're going to build the entire thing together, and then we have to build it all together and have it be perfect the first time. It's much harder to do. And so that's what I want to show here. See kind of these different, and in this one especially, you can see, you know, starting off with just these really actually quite low efficiency solar cells that are kind of scraps from cutting cables all the way down through kind of traditional space triple function solar cells, and iterating on a whole bunch of other things as well. And the other thing was then kind of rolling in tech demos, trying out new features and things like that on various different launches. Another thing that's not terribly as relevant for you guys, you'll be building kind of one, is thinking about building things from a scalability perspective and being able to build lots of spacecraft. And so that was a huge part of the thing, is a huge part of the thing at Planet, which is thinking about how you can be building hundreds of these things and integrating them and testing them and operating them. And even though you guys won't be building a lot of spacecraft, the thing that you should be really thinking about is how are you going to be able to test it, to debug it, to operate it. Building something that you can just design and build is kind of one thing, but you're going to be taking this thing apart and putting it back together so many times. So think about accessibility. So if you have, you know, for example, you've got your spacecraft, you've got some PCBs in your structure and stuff like that. Don't bury all the possible test points that you're going to want to have on your spacecraft, and make it so that you're going to have to like undo every single screw to get access to your flight computer, because you know what, things are going to go wrong. You're going to have to cope with that. So think about accessibility, how you can get access to your vehicle when you're building it. And one other thing I would consider is, again, on this whole idea of having a couple different versions of your vehicle, is a lot of times, I mean, especially because you are so volume constrained, there's only so much you can do for accessibility, is building what's called a flat sat. You need to take all of your boards and systems and kind of splay them out on a table, and you have non-flight, kind of longer than flight harnesses, and use that so you can poke at all the things while things are going on, and you can reprogram and stuff like that. So, and then for operation, again, think when you're designing your vehicle, when you're building your vehicle, how are you going to operate on orbit? What things are going to be available to you? What things are not going to be available to you? And make sure you can sit all that sort of stuff. All right, jumping a little bit into Astranis. Again, just wanted to hit on some of this kind of constant iteration. This was a very early version of our spacecraft that we designed. And then sort of key note here is that this had this deployable mesh dish, basically. A very complicated mechanism that we thought we needed. Kind of going in parallel with our development iteration on the first one, we realized that, oh, we actually don't need to have that sort of dish. And therefore we basically threw it away. We've done a lot of work on it, but the risk was so much higher and complexity was so much higher that throw that away and go on to something that was much simpler, and we ended up having just some patch antennas on the front. And sort of key takeaway I wanted to take from that was, even if you go down some of these paths, and you will, where it seems like the right thing to do, go down, you spend a whole bunch of effort in it. Don't fall into the sunk cost fallacy, just assuming that, oh, well, I spent a lot of time on it, I might as well see it through. You know, always be considering and always be reconsidering whether you should be changing and going to something else. Yeah.
How do you draw the line between tenacity and pushing through problems and deciding this is actually not the right way to do it?
That's a great question. It's so incredibly case by case. I would say the best thing there is when I was talking about advisors. They can help out a lot with that. It's so case by case, and it's incredibly experience based. So people that have been through this before and had to make so many of those decisions and seen which ones worked out and which ones didn't, because even the most experienced people are still going to be hitting wrong on that quite a bit, but just the more experience they have on, so they can provide you a lot of advice based on their experience on what works and what doesn't.
What about if you have an idea that you are convinced of the right way to go, and your advisor thinks it's not a good decision?
I mean, you guys are ultimately, it's your program, it's your project. Your advisors are there to provide you input, and you should be taking their input, but then otherwise making decisions to your program. Right. Then just wanted to show our cute little clean room. Again, the lesson I wanted to take here was being scrappy, which is that for our demo satellite, we have a real clean room now for our next satellite. But for our initial satellite, we built a nice hacky clean room that did a job quite well. And not that I'm saying you need a clean room, but I wanted to, unless you're building optical stuff, you honestly probably don't. There's nothing that's terribly degree sensitive for molten sort of things, and you're probably going to have to bake out. I don't know if the protocol requirements are, whether you have to do a bake out or not. There's like Nanoracks, which will deal with a lot of that stuff. Anyway, even if that was an issue, probably not a huge deal. But the one thing the clean room did that was, and we also didn't have an optical payload other than the star camera that we had on it. But the thing that this did for us that was great was just sort of the mindset. When you step into the shower curtain clean room, then you knew you were working on flight hardware. You treated things differently, and you made sure you had your gloves on. You made sure you had your ESD strap on, and that having a designated zone for your flight assembly and flight build and flight test, whether it's a clean room, and by the way, this just had basically positive pressure putting into it. So I don't know, it probably was 100K or better, even though it doesn't seem like it. But yeah, having a designated zone and making sure people are in the right mindset when they are building flight hardware is critical. When you're prototyping, it's a little bit different, but once you're really building your flight hardware, you can try this out if you're building a qualification set of hardware as well. And you know, something seems strange or something's broken, just take a step back. It's going to be okay. You're more likely to damage something in a rush trying to get it working than you are to step back, think about where things are. Delivery, we launched the space flight for this spacecraft on a PSLV, the Indian rocket. And since it was taking it and integrating it into Spencer, this Spencer is different from the ones that you guys will be using. I'll show you pictures of that one. And we realized that we neglected to actually show us coming out of our deployer. So I should grab that picture, but I did not. What is this, our new facility? All right, so some final thoughts I want to go through real quick, which I think I've probably, oops. Final thoughts. Simplicity is key. There's a lot of work in putting together a CubeSat. The design is going to seem really simple when you come up with a basic payload, one new CubeSat. It's going to seem really simple, but you really want simple. There's a lot more work that you're not considering, that you're not thinking about in building these things. If you're able to add features later, because things are just going awesome, then great. But I would start with the bare minimum set of things that you're able to do, and then build up from there. Talked about this earlier, build early, iterate often. Again, back on the keep it simple. Be realistic, don't spread yourself too thin. we really want you guys to be coming up with a payload that is novel and exciting, but novel and exciting doesn't have to mean complicated. So be reasonable about that, and then figure out the bare minimum requirements that are required for that for the rest of your bus, for the rest of the spacecraft to support that, and build that first. Maybe you can add more stuff later. Analysis is good. Testing is great. Fundamentally, analysis is subject to you knowing the right boundary conditions, you setting the right properties, you knowing how to use the tool properly, none of which are givens even for very experienced engineers. So you really want to be getting ASAP over to test. But analysis is great to reduce the number of cycles you have to do. So it's a balance, but ultimately testing is what matters. And calculating budgets. And a little bit long, and happy to, after we finish the rest of them, then can do more Q&A.
Who are you?
I am Ryan, co-founder and CTO of Astranis. Yes.
So I had a question for attitude determination control systems. What are you using an apparatus, or what kind of apparatus are you using to check for the accuracy of like your magnetometer sensors and determination control?
For the most part, in terms of accuracy of the various attitude determination things, we based off the data sheet component. And that is fine. Cool.
Now we get to get shown up by probably way too cool girls.
Hey guys, my name's Abby Dickus. I do marketing over at Nanoracks. What I'm going to start with is just sort of framing the story for you guys. I think as John made a really good point of sharing, telling your story, especially as you go out and fundraise, is super important. And I want to make sure you guys are aware of what's going on in the big picture and sort of talk specifically about Nanoracks. But you guys are at a really crucial point in space history, which you may or may not know. I mean, we're in this commercial revolution, and you guys are now officially going to be a part of that. And so hopefully this can help you guys as you frame your story, get a bigger picture of what's going on, and of course, boost up Nanoracks as you go into your fundraising too. We've got a pretty good rep in the industry, so feel free to leverage our name. We're proud of that. And before I forget, thinking about the marketing side of things, check out the EQUISAT website. We flew their kids, EQUISAT. We flew them through the NASA Alana program. They're a student CubeSat from Brown University, and they have an amazing website. So use them as a good example. I wanted to see that before I forgot. How many people are familiar with Nanoracks before I get started? Great, fantastic. We were founded back in 2009 with this idea of making space much more accessible. I mean, as you guys can imagine, 10 years ago, you pay millions of dollars, maybe 3, maybe 5 years if you were lucky to get to space. And that's just not feasible, especially for students. So our goal was really to change how that all operated. First, customers were students, and students are still probably our largest customer base. We've probably flown over 500 student experiments, from satellites to mixture tubes to crazy electronics, you name it. Our youngest CubeSat was actually an elementary school satellite. It's really cute, yeah. Connor's got some good stories about them. I mean, they were as young as kindergarten. They were cheering on this fit check. It was really incredible. And so everyone sort of knows us as this basic, access to ISS. That's sort of what people know us as. But we actually have a lot more going on. Our long-term vision is that we're a destination company. The ISS is one of our destinations. And so what we're actually looking at doing is repurposing upper stages of launch vehicles and turning those into commercial space stations, which is much bigger than just one CubeSat, but we're going to need a lot of CubeSats on those space stations. So think of us as you guys graduate and start your own companies. And so we're looking to populate the solar system and keep these, have the customer in mind. Maybe it's for research, maybe it's for satellites, maybe it's for tourists. The future will tell us what we've got going on. But that's really our big picture. We're much more than just shooting a satellite off the station, even though that's a really important part of our business model. We were able to drive costs down by standardizing hardware, as simple as being able to use a USB plug for getting your power and data. That was not a thing, and now all of a sudden that is. And so you can actually be able to use a common interface and actually get your research done. yeah, like I said, that was not a thing 10, 15 years ago, and so it seems like a really simple idea, but we were the ones who actually went out there and changed that notion. Our platforms go beyond just the ISS. We also launch on PSLV now. We do Blue Origin. We do all their payload integration. So down the line, if you guys want to start testing satellite parts in a suborbital flight, you can come to Nanoracks for that too. We've got partnerships with Moon Express. We're doing lunar stuff. Like I said, we're building commercial stations, and in about a year, we'll be launching the first ever view of satellite per deployment cycle. It's wild. You guys could all fly CubeSats and get them all deployed at once. It's gonna be crazy. And so, as in a written form, that's everything we do. You guys are gonna be focused right there, but that's everything we've got going on. There's literally never a quiet day in our office. Usually you're on the road, here, integrating. I don't know, Connor was gone for like 4 weeks at a time, I think, in the last month.
That's true.
Yeah. I imagine, honestly, like half of you will probably start companies in the next 5 years. I feel like that's what everyone's doing. That's so cool, and that there's these opportunities for you guys to do that. Get a Space Act agreement. That is literally the Bible of Nanoracks. That's what gives us access to all of NASA's resources and facilities. I mean, we are probably one of very few commercial companies that has direct access to talk to the astronauts on station. So whenever they're running our experiments within our Houston office, we have this awesome operations room, and we're directly talking to the astronauts to get our research done and make sure they're doing it right for our customers. Astronauts have ruined things before, but you know, they're people too. So we tell them, you know, don't turn the wrench that way, turn it that way. It's cool. But yeah, so the Space Act agreement gets us access on SpaceX, Northrop Grumman, Soyuz, Progress, ATV, HTV. We've flown on all of them. And that's really the binding document that lets Nanoracks exist as a company. So it's just an important thing to be aware of. We have a ton of customers. This is just a small sampling of them, and we're really proud. You know, like I said, we've flown over 500 student experiments. We have Astranis up there, Made in Space, Boeing, you know, Millennium, which was bought by Boeing, Planet Spire. We know them all, and so Connor has a lot of great tips to give you guys on the do's and don'ts of flying a CubeSat, because he has seen the best and he's seen the worst. And this is, again, I'm going to go through this all really quickly, but these are just all the platforms we have. So you guys will be doing the CubeSat deployment on the very top. We also deploy satellites from the outside of Cygnus, which is super cool. One Cygnus leaves station, bumps up to between 450 and 500 kilometers, and then we shoot them directly off the spacecraft before it burns up. We have double wide standard, and we also do up to 90 kilograms-ish with our microsat deployer. We also do a ton of stuff inside the station, mixture tubes, nanolabs are those boxes you probably, I don't know if you guys follow us on Twitter, you guys have seen some pictures of those. Plate reader for biological research, all kinds of cool stuff to keep in mind. Yeah.
Oh, sorry for stopping.
No, it's fine.
What altitude are you usually deploying at?
ISS,
altitude is about 400
yeah,
kilometers.
ISS is 400. That's what you guys will be. It's about 400, what, 51 degrees?
51.6.
Yeah. Again, this is really quick on our airlock. So we just passed our CDR 3 days ago. So it's really exciting. And we're manifest on SpaceX 19 officially now. That'll be launching end of 2019, maybe early 2020, depending on the launch schedule. Like I said, this is going to deploy hundreds of views of CubeSats. We currently deploy through the Japanese airlock on station, and they've been awesome, awesome partners. But it is a government-run facility, and Nanoracks moves far too fast for that. And we needed a lot more capacities. This is about 5 times the size, so it's going to be a really exciting project. And then the last part is, of course, like I said, we're building these commercial stations, right now, the upper stages of launch vehicles are just burned up right when they're done, and they're these multi-million-dollar pieces of hardware that are, I don't know, what, 4 or 5 stories tall. It's crazy, what a waste of money. And so we're working on repurposing those in orbit using robotics, autonomous software, even astronauts. It's going to be a really cool program, so keep your eyes out for that. Yeah.
How would you all acquire those stages?
We are already in work on that. We have some agreements I can't quite talk about yet. But I mean, we've said pretty publicly we're working with ULA on this program, so you can imagine Atlas 5 and a few others. And we actually have some specific launches that we're targeting to use those specific upper stages.
Interested. When do you feel robots are the best for repurposing the rocks, and when do you need a human in the loop actually doing that on orbit labor?
It depends. So we're looking at 2 options. One where actually births to ISS, there's sort of that open node that a few of us are fighting over, I should say. We think there should actually be multiple ports for multiple stations, right? We're here to build an ecosystem, not have a monopoly. In that case, it'd be great to have astronauts because we're leveraging the infrastructure of the ISS. But if we want to send one out to GEO and who knows where, we have some time before people get out there. So robots are certainly going to lend us a helping hand in that case. Awesome. I think that's my last. Now you know a little bit about Nanoracks. I'm going to pass it off to Connor. Like I said, he has literally, every single satellite we've launched in the last 5 years has gone through his oversight. So he's got a lot to share.
My turn now?
It's your turn.
Okay.
Got notebooks and handouts for you guys.
All right, well, thanks for coming, guys. Tough act to follow, but I'll do my best. So yeah, like Abby said, I'm the director of payloads at Nanoracks. I've been focusing on our external payloads, which is what we refer to as all of the payloads that go into the space vacuum. So that's mostly CubeSats, but we also have a hosted payload platform on the space station where we provide power and data services to payloads that are just bolted on the outside of the space station. So I started at Nanoracks about January 2014. I was fresh out of school, and so my entire career now, I'm coming up on my 5-year work anniversary, has been on CubeSats, which is crazy because when I was in high school, this commercial industry for CubeSats didn't even exist. So when I see people like you guys in university and high school students that don't know what they want to do when they're older, don't worry about it, because the industry you might be in might not exist yet. We're at a really interesting inflection point, not just in the space industry, but in the technology industry. And space is really one of those industries that's benefiting from that. We want to be a space station company one day, but what really drives my passion and why I'm so invested in the CubeSat industry is I'm passionate about the commercialization of space. I think satellites is one of the few really proven commercial markets for space, and the satellite industry has been around for years, decades. But the small satellite booms, you're just coming in at just the right time. So I have quite a few experiences launching CubeSats specifically to the ISS, which as a manned platform has very stringent safety requirements. So what I'm going to focus on today, as all of you are thinking about submitting proposals to this RFP, is some lessons learned that I've seen working with so many teams. A tremendous amount of our customers are university students. NASA Launch Services Program is an excellent vehicle to fund university satellites. And being part of something like this with Astranis, offering a launch to a university team, is just such a fantastic opportunity to get more students engaged and get more people coming into this industry. So I'll share with you, the lessons learned as best I can. I don't build the satellites. Ryan gave you all that details. I actually used to work with Ryan when he was at Planet, when we were launching as many doves as we could into space back in 2014 through the 2017 timeframe. So what we call NRCSD, that's just Nanoracks CubeSat Deployer. It's a 6U dispenser that we assemble into quad packs, 24U total, 48U per airlock cycle. The reason it's such a strange form factor, I don't think I've ever seen another 6U in this form factor, is because we're maximizing the volume available on the Japanese airlock slide table, like super specific, how much we wanted to maximize the amount of CubeSats we can get through the Japanese airlock. So this is actually the platform that the ultimate winner of this RFP will be launching on. We have, just 2 weeks ago, I handed over our 15th CubeSat mission using this platform. Missions based on airlock cycles. We've actually handed over 18, but there's been a couple launch failures over the years. But knock on wood, it's been a while, and things are going well. So, like we touched on, the ISS altitude hovers right around 400 kilometers. That's where they've been flying it lately. We do have some other capabilities that go above ISS and off ISS options, like sun-synchronous flights available, but we'll focus on the ISS today. And if you can build and design a CubeSat that meets ISS requirements, odds are, except for a few exceptions, that you'll meet requirements of other vehicles because it's a manned platform. So, a little bit about the ConOps. So, all of the design and build and integration will be the responsibility of the CubeSat teams to our interface definitions and the requirements of the program. Once you have built your satellite and you've tested it, we've performed the necessary fit checks, and you've passed everything and you've been certified from NASA for safety, you will be packed and integrated into the deployer. That happens in Houston, Texas. That's where our primary office is. Abby and myself are based in Washington, D.C. That's where we do a lot of our program management, mission management. I'll put a plug in that we're always hiring, so keep us in mind as you guys come to the workforce. Shoot.
If our university is very close to y'all, how much can we annoy you?
You can annoy us all you want. Whether I'll respond to your emails is another thing. But yeah, so where do you go to school?
Texas A&M University.
Oh, awesome. We have a lot of A&M grads. Yeah, annoy us all you want. I'm in DC, so I don't care how much you annoy you. I'm actually based at Johnson Space Center. I spend a ton of time down in Houston. I was just in Houston for like Abby said, I think 3 of the last 4 weeks working on our SpaceX 16 mission. So yeah, bug us all you want. We would love to fly an A&M satellite. So anyways, once we're integrated into the dispensers and we assemble the deployers into the quad packs, we launch in the soft stow environment, they call it. So you can see there's a quad pack. It's in bubble wrap, foam, packed inside a cargo transfer bag. It makes for a pretty soft ride. Now, foam isn't necessarily just mean it's easier. It does actually amplify the acceleration loads in the lower frequencies, but overall it makes for a pretty easy ride. We can do testing that simulates this environment, and there's certain vibration test profiles, but at the end of the day, it's a pretty gentle ride. Once you get to the space station, the astronaut actually installs the integrated CubeSat deployer assembly onto the airlock slide table. So there you can see the slide table extended after the mission's done, but basically those are 8 of our 6U deployers go into the airlock. Looks like science fiction, but once they're outside, the robotic arm grapples it, positions it for deployment, and one by one we command them to deploy from the space station. The person that hits the button is actually in Scuba, Japan, but we're in the loop with the astronauts and Marshall Space Flight Center to command these. Once we've deployed all the satellites on a given mission, it's watch, rinse, repeat. We bring them inside. We typically downmask the deployers on the SpaceX Dragon vehicle and refly them again. So, like I said, ISS is an interesting platform. It's probably the strangest way to deploy CubeSats in the world. It doesn't make a ton of sense, but this is, given the resources that we have, it's actually a fantastic way. And so we've deployed over, I think it's 230 satellites across our various platforms, over 200 using our ISS deployments, approximately 30 from the Cygnus deployer. And so we have a ton of experience working with these teams. I'm going to focus today on some of the unique launch requirements that you should keep in mind as you design your system, particularly the various subsystems. Oftentimes the payload isn't what presents the hazard. It's things like the batteries, the transmitters. Some of the high-power RF transmitters can pose hazards to the station crew, things like that. So it's important that you design that high-level system architecture to inhibit the system when it's in the box, which is actually pretty easy to do, but you'd be amazed how often you can overlook certain aspects of that and cause yourself problems down the road. So obviously battery testing is a big one on the space station. One of the #1 concerns, I think the top 2 concerns for the space station program from the safety environment is obviously debris hit and a lithium battery runaway event causing a fire. Things in the news like the Samsungs and the hoverboards don't help. They're obviously a risk-averse program, as they should be, but for that reason we do have pretty extensive testing required of lithium-ion batteries, and like Ryan touched on earlier, it's all doable, but you got to make sure you have the right protection circuitry in place. Some of these tests, if you didn't have the right protection circuitry, you will start a fire because you'll basically be driving it into a short condition or an overvoltage case or under voltage. We also require, I think maybe the most unique requirement about our launch is the amount of inhibits we require, which is basically how many switches on your satellite keep it powered off when it's inside the deployer. We require 3 as a baseline. Most would require 2 or 1, most launch vehicles. The reason we require 3 is because it's what they call 2-fault tolerant. You could have 2 of your switches fail and you're still powered off, and that's to protect against any potential hazard that the satellite might pose to the crew. You know, there's some materials considerations, obviously. Flammability is of concern, hazardous materials. There are ways to fly them. If you have a really novel idea that it requires use of a hazardous material, that's okay. Just keep in mind, depending on the toxicity level, you're going to have to require more levels of containment. Basically having that redundant, so if one of your boxes fails, it's a box within a box, you know what I mean? So like we've had CubeSats with atomic clocks, with radioactive materials that we've had to have levels of containment for, things like that. That's the major outline. So today I'll talk a little bit about lessons learned, kind of where I see the biggest issues, where I see teams get hung up. That's in the regulatory licensing process. That's just a nightmare that you're all going to have to learn how to deal with. There's no easy way around that. The rules seem to always be changing. I'll give the best advice I can, but it's engage often, engage early, and make sure that you're not putting yourself into a corner by selecting some frequency that you really don't need, but you're going to have to require a ton of extra coordination to utilize. We have the battery testing, we have the inhibits, mission design. Ryan hit on some good points, so I won't be too redundant there. Material selection, and it's a lot of paperwork. Let's start with designing your mission. There's a cool picture of me and my colleague Henry, probably pretending to work. You guys have an interesting phase where you have until, I believe it's May, to submit your proposal, but you have to get to PDR, and so you really have to flesh out the design. So when building a CubeSat, the biggest issue I see with new teams is they get a little over-ambitious, particularly with the subsystems. First, start from scratch. What's your idea? What's your novel idea? What's going to change? Like, it can be simple. Do your research, talk to people. There's so many universities now that have flown satellites. I have a list of 30. You know, you can go talk to those people. I know people that are willing to advise other people who stumbled through this FCC process on their own the first time. There's no need for everyone to stumble through it. Not only is it inefficient for you, it's inefficient for the regulatory bodies, and it kind of can grind them to a halt too. So yeah, don't underestimate that. Material selection is something of interest. I unfortunately have some specific materials requirements for ISS that are a little outdated, but that are still hard requirements for the ISS program, like certain aluminum alloys that are deemed susceptible to stress corrosion. That it's obviously not an issue, you're anodizing them, but I still have to do a unique hazard report if you use that. So don't do that. Read my requirements document. Go, and it's not nothing obscure, but just use the right stuff. It's kind of interesting. We actually don't require a bakeout for ISS, but we do require a detailed bill of materials, and so outgassing is something you need to watch out for. Basically, when you put something in a vacuum, it's especially plastics, non-metals, they're gonna gas, and so people run into trouble with COTS electronics, particularly like PVC coated cables. PVC coating is like an X rating in NASA. They do not fly PVC, but it's like a lot of those ribbon cables and stuff like that that you'll see on off-the-shelf boards have that. There's tricks, you can encapsulate it and stuff like that, but you gotta try to avoid it. Most of the COTS suppliers out there that are gonna provide you your power systems and stuff know this stuff. But there's a lot of new suppliers in the market, you know. Someone told me there's over 50 CubeSat component provider companies now, which is kind of crazy. Maybe you guys will go start some more. So some are much more established than others. Go ahead, Ryan.
You can also buy PTFE coated encapsulated cables off DigiKey.
Yeah, exactly.
They're a lot more expensive than PVC, but
PTFE is what we're looking for, you know. So that's the stuff. That's the good stuff. Yeah, it's a lot more expensive, but we're probably not crazy.
it's not going to drive your program.
Yeah, it won't be your number one budget item. So just keep an eye out for that. Reentry survivability. I have another satellite that went through this issue where inside it was a 6U satellite. Inside the, we're running out of time, so I'll just wrap it up in a couple minutes. But keep this in mind too. You have to do an orbital debris analysis report showing that your satellite won't survive reentry and pose a risk to those on the ground. There's specific NASA standards for this. I think they're outlined in the RFP. And so we had a satellite that put a bunch of titanium bracketry inside the bus. I think they were trying to shave on mass. And so then the FCC saw this, that they had greater than 15 joules of energy when they re-entered, and it ground their application to a halt. They said, you need to go get liability insurance to ensure you're not gonna, you know, kill someone on the ground. And then they tried to do that, and then they couldn't satisfy the commission with that. And so they ended up having to take the whole satellite apart, replace those brackets with aluminum, and miss their launch and go later. So all sorts of little stuff like that. Keep in mind all the requirements. We did our best to summarize all the requirements in our document. The RFP points out some NASA standards that should be adhered to. You should be in good shape, but when in doubt, just ask your launch provider, ask someone like me, or get in touch with Astranis, or just ask, because we can really help you avoid some of those downstream issues. I'm basically done. I've talked about battery testing. We've talked about, some more battery testing. paperwork I think I've touched on enough, do test plans, writing a decent report. I get so many garbage reports coming from teams. It's like, dude, come on, you know how to write a test report, right? Here's what I did, here's the results, here's the little conclusion. I wrote lab reports in college. I know you guys have to too. Just take it seriously. It's a professional project. It's really just like an effort. I know you're all smart, so just take that little bit of extra effort and put it on Drive, and then think about the next team that's going to follow when you guys all graduate and enter the industry. Don't you want to leave a nice file repository so that someone can actually build on the work you do? That's really what you ought to be thinking about and being future leaders in this industry. So I know it's paperwork, but take a little time and attention, and it goes a long way. And we don't need to talk about this. The schedule's outlined in the RFP. We typically take a year to get things approved. We've done it a whole lot faster. It depends on how complex the system is, but keep in mind, this is my favorite kind of program because you see our requirements as you design. Usually I get a CubeSat, here it's on the shelf, can you fly it to the ISS, and it doesn't meet any of my requirements, and then it's a constant battle of, okay, what waivers can I process versus what do I really need to make you go do? Yeah, you gotta go replace that PVC cable, et cetera, et cetera. So,
for those, sorry, I know
Go
we're
for it.
short on time, but for those groups that come to you and like, hey, I have this thing, can you launch it? Do you have any recommendations for those teams? Like, so for example, are your launch conditions, your RFPs, are those available for anyone to look at?
our interface definitions document's on our website. It's available. The RFP, I believe, is posted online as well. So yeah, in short, our requirements are available. There's a couple things, secret sauce we try not to put out there because we're a services company. A lot of our expertise is getting things flown to the ISS. It's like a strange expertise to have, but that's what we have. So, but yeah, absolutely. Our core requirements are posted publicly. So to answer that question, we do our best to fly them as is because we're in the customer industry. We make money when we fly payloads. So, but yeah, sometimes it's just something's got to give. So. So I think we got some time, John, for questions.
Questions, yeah. That's the only reason we're
cool.
But thank you so much also. So yeah, this is the opportunity. If you have questions about the RFP that you have not seen yet, if you have questions specifically for Ryan, Abby, or Connor, or myself, we have tried to weight this competition for new ideas and people that don't necessarily have experience but want to get the experience and are serious about it. Ultimately, this is for you. Like we want you to work for us. we want you to get the hands-on experience that is pretty much required industry-wide. I don't think Ryan would have hired me if I didn't have hands-on experience, and I'm doing business development procurement.
That is actually the biggest thing that we see, opportunity for that plug of when we see applications coming in. I saw this at Planet, I see this here, or I see this at Astranis, which is people that just don't have extracurricular activities. They haven't had a project they've worked on. And by the way, just the projects that go with classes are cool, but not great.
I gotta get started for that. So we get 20 resumes a year. Every time we put out a little call, we get 20, 30, 40 resumes from the University of Maryland. Every kid, quadcopter project, and then, this coursework. And it's like, those immediately go, no offense, go in the trash because every single, you were required to do the project. So it's like, but if someone said, I led my own CubeSat development project, that's gonna stand out. So this is a great opportunity for you.
This is the stuff that gets you noticed. And also just not just being there, but driving things and owning things and stuff like that. Because the fact that you have it on your resume gets you the phone screen, but then what gets you past the phone screen is that you can talk intelligently about these trays that you made, these designs that you made, things that you built from scratch, whether it flew or not.
So in school, faking it until you make it actually is a good thing to get you to the point where you can start leading and doing projects, but you actually have to do the projects. It only gets you so far, and people can see through bullshit
Yeah, we'll
Very,
know if you were
very
just
different.
going to the
Yeah.
meetings, or if you're,
What?
we'll know if you were just
Yeah.
going to the meetings and put it on your resume.
Yeah.
We're
We'll
the
find that out.
first line of defense of applications,
Yeah.
so we know.
We do lots of phone screens per week.
Yeah, and that's not to intimidate or dissuade or anything like that. It just
No, you're all in a great spot.
yeah, exactly.
The
Yeah,
fact that you
you're
are here puts you in a very good position. The fact that you're even here considering doing projects like this. And this is something that you won't realize until you are hiring people yourselves. But, yeah.
So I actually have a question about that. I spent like 18 months trying to get my school to let us have a rocketry team, and then right when it started, I had to leave and with everything. So I don't have the actual rocket building part in my resume, just everything that led up to the school finally saying, okay, we're gonna help you do this. Does that count for anything?
Absolutely.
No, it's strike from the record.
That's a really great question, and all of that stuff is hands-on experience to a certain extent. It might not be building, but being able to go through. Connor said the regulatory is the number one reason that people don't launch on time or at all. That's super important.
Being able
Like,
to just get things done and navigate challenging situations and handle all that sort of stuff is huge.
yeah, believe it or not, organizations that you work for after school are still made up of people. And so being able to deal with those people and get things done, 100%.
It's important to know how to write about what you're doing also. Like there are real people who are reading this, you have to be able to market yourself essentially and explain that to the person who's reading your resume.
Hey.
Would you guys be willing to share the presentations from today with us?
I think we can just do some simple scrubbing and put it up next to the RFP. Cool.
So like, what's the absolute extent at which Nanoracks and Astranis are kind of helping this project? So I know you guys are paying for the launch, which is great, like already pretty much, but like is there going to be like a contact person that people can reach out to, or like what, are you supplying any other like services?
Yeah, so we're going to find mentors for the teams. That's why notice of intent is very, very important, because if we have to go find 40 mentors, it's a lot harder than if we have to find 3, and I really hope a lot more than 3 show up. But I will be point of contact. Astranis is about 6 full-time jobs, so it's I won't be the end-all be-all, but we're going to be here. We love speaking to students. Yeah, so we'll support.
To the team that gets awarded the launch,
yeah.
Nanoracks gets turned on full time, just like any other CubeSat. So,
Yeah.
you know, you'll be assigned a mission manager, whether it be myself or one of the folks on my team, and they'd be talking to you every week or two about all the requirements, walking you through the whole process. I didn't touch a lot on our services, but it's our job to interface with NASA and get you approved through safety. We'll tell you what data we need, that sort of stuff.
And they're the people that do it. So that
Yeah, just to jump back really quickly to experience. So we have a rocketry team at our school. How do you feel about CubeSat experience versus just general building experience?
you're building stuff, man.
If we're talking generically about the job applications thing, then yeah, build things.
Yeah.
It doesn't have to be space.
If you're talking about experience with regard to the RFP, you're building stuff. That's awesome. It helps. We did put a requirement in there that's kind of a binary scoring, whether you have the letters of commitment from advisors that will be able to help you see this through to the end, whether the university or commercial companies or anything like that, and that's very important. There's weighting in the RFP with regard to that. But it's a low percentage, but it's very, very important, and it's an easy one to just get knocked off.
Do you all prioritize hiring certain grade levels over others?
That is also in the RFP. We would love for masters and advanced degree students to participate in this. We do want that. We've weighted it so that undergraduates have a small edge over that, because obviously it's easier to have experience after you've either gone to a job and then graduate school or anything like that. But a healthy mix is great. If it's fully undergraduate, that's great. And if it's all master's students, there's a tiny ding to the. Yeah.
So for the teams that pre-registered already, what kind of time frame should we expect to hear back in terms of like the structure of competition and like official registration, stuff like that?
That's in the RFP. Yeah,
Okay.
that's all in the RFP. It's up now. And there will be like a 1.1, 1.2, again, based on your questions. So there's a 2-week question asking period. Ask them. They're going into a spreadsheet right now, and then we'll filter through if yours doesn't get asked or if it's already available in the RFP. We're not going to answer it. Attention to detail. Sorry. But if it's something that we're like, oh crap, we didn't clarify that. Obviously, we'll probably change the RFP to accommodate that. But it's should be in the RFP and online. Yeah.
How are you finding mentors?
Like
from where, I guess?
Mostly Facebook Messenger. Yeah, but we're gonna try to get some people that are super passionate about helping students, which that's what makes the space industry great, is there's a plethora of them. So reaching out to colleagues, friends that have the time to invest. Yeah. And they'll be people like us.
So we have a team that's already developing CubeSat, but we just don't have a whole lot of guidance because this is the first CubeSat of our university, and then our university doesn't really focus on satellites. So we don't have a ton of guidance. Can we go through your program to try to help us in our design phase, since we've already started for a while now, but like I caught the end of your presentation, I'm pretty sure we're missing some of the requirements for the launch. Our understanding of that, like, can we still get advice from you guys, even though we're not part of the competition?
So, loosely, like if we, because it's essentially us doing it on our sides. So we can try to help you find people, but I would highly recommend going out and finding those advisors that are required. LinkedIn skills, getting strong is great. Being able to cold reach out to people that build CubeSats at Planet Spire, other universities. This is a competition to see who will launch, but it should be a sharing of ideas and everything. Peer mentoring is a great and wonderful thing. But yeah, we'll have an avenue for you to reach out to us with questions and advice like that.
Is there any reason not to be part of the competition?
Can we be part of the competition even though we've already started developing?
Yep. Yeah.
Okay.
There's we have a small a small percentage is weighted towards new designs and builds just because full life cycle. But yeah, absolutely. Yeah.
What school are you from?
East Irvine.
Okay.
Awesome.
So you're setting up this competition to give people an opportunity to build and get this experience. How do you weigh that opportunity versus the capabilities a university might already have? So for example, are you here to give a university the first CubeSat, or would you look at a university that can churn out CubeSats on a regular basis and say,
so yeah, great question. And going back to that, we did put a bit of weighting towards new CubeSat builds and everything. That being said, capability is very, very important. But we'd like to see some people that have never built a CubeSat get that experience. Anything else?
Slightly different. Just jumping back to my presentation, I realized something important that I forgot to say, which was on the subsystems chunk. I left out TT&C, telemetry tracking and command. Something very important to think about that might be forgotten on both the space side and on the ground side, which is that you need radio on the satellite, and you need that radio to absolutely work, because if that doesn't work, then you have no ability to debug anything else on the satellite. Probably the most important thing. And then you also need, and this is just largely a logistical thing and a money thing, you need to have something on the ground somewhere that can talk to your satellite. And so that's another thing that you have to procure.
Also a ground station.
Yes. Yeah. And so you can rent access to ground stations, you don't have to build one. You can even you could build one and put it on the roof of your building. But I would recommend renting space. There's a lot of services these days.
There's also, it's not as intimidating. One of the companies that I used to work for, the first time they contacted their satellite, it was literally a dude with a Yagi antenna just being like, it's supposed to be there, beep, beep, beep. I think it was the call down was the Imperial March from
Right.
Star Wars.
Yeah, low data rate omni-ish antennas help you out, which is another thing. Make sure your satellite, just like do your TT&C with an omnidirectional or pseudo omnidirectional antenna.
What does TTT stand for?
Telemetry tracking command. And yes, please put an omnidirectional antenna on your satellite. You don't need super high data rate. Yeah, and then for the radio, just buy something. There's plenty of places where you can buy a radio. If you want to not buy a radio, the other thing is go to Planet's website, and there's a radio that is referenced on their website that may be usable for satellite applications. And yes.
Yeah. Yeah.
The only reason I'm being cagey is for export control reasons. You can use it.
Is there time we could talk to you guys afterwards about specifics?
Yep, I'm happy to. The only thing I would say is definitely want to get to lunch, because that's super important, not just because I love food, but because I think it's state of SEDS and COC and elections and things like that. So that's, but I'll be around this entire weekend, so come up, and I don't know when y'all are leaving, hopefully not soon. But
Not soon, so.
Oh, okay.
Find us
after this if you
Yeah,
want.
we'll give our cards and everything.
Yeah. Yep. Cool. Thank you all for showing up.